Hello there guys, welcome back to another epic inexorable maths video. In this video, we're going to show that the area of an ellipse is a times b times pi, where a is one radius and b is the other. So these are two perpendicular kind of radii, where in this case, but it's without loss of generality, we're saying that A is bigger than B. So A is the major radius and B is the minor, okay? So the distance from 0 to here is B, and from 0 to A is obviously just A. We know, well, you may know, you may not know, but I'll tell you, the Cartesian equation of an ellipse is given like this. So x squared over a squared plus y squared over b squared is always equal to 1. That's the Cartesian equation of an ellipse. Now, you can do this with parametric integration, but we're just going to directly do it because it's a bit longer, it's just a bit of an exercise. The parametric method is definitely a bit easier, but I've not done any of those videos yet, and I want to kind of introduce that topic and then we'll do videos on it. So we're going to integrate this in a more kind of conventional, typical way. So first of all, we're going to take the equation of the ellipse and we're going to rearrange it to get y on its own. Okay, that's what we're going to do. Okay, so maybe we'll take away x squared over a squared from both sides. We have y squared over b squared equals 1 minus x squared over a squared. Okay, and then we can multiply both sides by b squared. So y squared equals b squared times 1 minus x squared over a squared, like this. And then we'll take the square root of both sides. We have to be a little bit careful, of course, because y can be negative, so we can't really, we're going to end up with a slight issue if we just directly take the square root. But I'm going to do it anyway, just for a second. So square root of both sides, y is equal to the square root of b squared times 1 minus x squared over a squared, like this. Now, technically, it should be a plus or minus, but I don't want to get into the plus or minus stuff. So what I'm going to do is I'm going to say, well, it's symmetrical. The ellipse is symmetrical above and below the x-axis. So why don't I just calculate the area above the x-axis, and then I don't need to worry about the minus, and I'll just double my answer at the end because there's an above and a below, and they have the same area. So I'll just calculate above, and then I'll double it at the end. Okay, so we don't need to worry about the minus. Lovely. Okay, and we can simplify this ever so slightly more by just, instead of writing this as the square root of b squared times 1 minus x squared over a squared, I'm going to split the square roots up. We have b squared multiplied by this bracket here. So this can be written as the square root of b squared, which is just b, times the square root of 1 minus x squared over a squared, just like that. Okay, cool. Now we can try to integrate. So I'm going to kind of do this in one column, and then I'm going to come and do it here, just so that we have enough space. So we're going to do the integral of y with respect to x. So that's going to be the integral of b times the square root of 1 minus x squared over a squared, like this, with respect to x. Now you might say, this is a slightly difficult integral. You might also say, what about the limits? Well, for the limits, we're integrating along the x-axis, so we can integrate from minus a to a. But guys, I'm going to do another thing to make the computation a bit more straightforward. What if, because technically this is what you would call an even function with respect to x, what if we just integrated from 0 to a, basically just this top right quadrant, and then times the answer not by 2 because we were doing top and bottom. Why don't we times it by 4 because we're only getting the top quarter, but all the quarters are the same. So at the moment, we're just trying to get this area, okay? And the reason for that is it lets me make the limits easier. So the limits can just be from 0 to a rather than from minus a to a. Doesn't make things too much easier, but just it's a little bit useful. So we're going to do this, we're going to get this area here, and then we're going to multiply our answer at the end by the number 4, because there's 4 quarters, 4 quadrants. Okay, now the integral itself is a little bit, maybe I might say clandestine, okay? It's a little bit suspect, it's a little bit spooky, but it's not that bad, guys, because we can do a trig substitution, okay? So if you've not seen this before, this might seem really weird, But we can let x equal either a times cos theta or a times sine theta, okay? I'm just going to let x equal a cos theta because I believe the working out will be slightly nicer, but I don't think it makes any difference from what I can deduce. Excuse me. I think cos is better. I think cos is better. So a cos u, but it doesn't actually matter. So now you'll see what happens. And you could have done theta or u, it doesn't, I'll just use u, doesn't matter. Okay, so then dx du is going to be the derivative of a cos u, which is minus a sine u, okay? And then we're going to rewrite our integral. We'll do the limits in just a second, and we'll have b times the square root of, and you're going to see why this substitution is so good, because you might be still thinking that's so random, but watch, okay? We have 1 minus x squared. X squared is a squared cos squared u, so a squared cos squared u, and it's divided by a squared. Okay, and you can see that the a squareds cancel out there. And also we're multiplying by dx. We know that dx is minus a sine u du. So times minus a sine u du. Okay, cool. Now, this is going, and let's do the limits now actually, let's do the limits now. So limit-wise, what's happening? So the integral from 0 to a, those are x limits. If we just very quickly go up here, I might have to rub this off a little bit later to make some space, but our x limits are currently 0 and a. Let's just get u on its own for a second to work out what the limits should be. So divide both sides of this by a. We have x over a equals cos u. And then inverse cos, right? So inverse cos both sides, we would have u equals inverse cos of x over a. Okay, so if x is 0, then we have inverse cos of 0 over a, so inverse cos of 0. And inverse cos of 0 is pi over 2. So the lower limit will be pi over 2. Okay, if x is a, then we have inverse cos of a over a, which is inverse cos of 1, which is 0. So the upper limit will be 0. So it's a little bit weird that the upper limit is actually a smaller number than the lower, but that's actually fine. It's okay. All right, cool. So I'm just going to rub this off because I know that we're going to need the space in a moment. And actually, yeah, let me just come up here now. So rewriting this line, maybe a bit of simplifying. We have the integral from pi over 2 to 0 of b times the square root of 1 minus cos squared u. But guys, what is 1 minus cos squared u? What is 1 minus cos squared u? Remember that sine squared plus cos squared is 1. So 1 minus cos squared u, hopefully you can see, that would be sine squared. But then we're taking the square root of it. So we just have sine, okay? So it's b times sine u times minus a times another sine u, okay? So that's going to be b, I'll put the minus on the outside, minus b times a sine squared u du, okay? And then what I'm going to do, guys, is just to, and this is an a, it looks a little bit, I don't know what that looks like. It looks like there's a subtraction sign there, okay? What I'm going to do is I'm going to swap the limits and get rid of the minus sign, just because it's going to make the working out maybe slightly simpler. So the minus sign is gone, and I'm going to swap the order of the limits around. So I'm going to go from 0 to pi over 2. You're allowed to do that. If you swap the limits, just times the whole integral by minus 1, that's completely fine. Okay, now this is not looking terrible, but we could definitely do better. So what should we do next? Well, sine squared is it's not really possible to directly integrate, but luckily we have the double angle formulae, which you'll see are actually, is going to help us quite a lot. So we know that one thing that we can write about the double angle formulae is that cos of 2u is the same as 1 minus 2 sine squared u. Okay, so that means that sine squared u on its own, sine squared u, if we move that to the other side, move the cos 2u to the other side, we'd get a half minus a half cos 2u. So we can replace sine squared with a half minus half cos 2u. The reason we do that is because we can integrate this, but we can't integrate sine squared u very easily. So this is the integral from 0 to pi over 2 of b times a times 1/2 minus 1/2 cos 2u, close brackets, du. Okay, now let's just take some stuff out to make our lives a bit easier. Let's take out the b, let's take out the a, and let's take out a factor of a half. So this is ba over 2, integral from 0 to pi over 2 of 1 minus cos 2u, just to keep things nice and simple. Okay, we're almost done. Now we just have to integrate. We can directly integrate now. So 1 integrates to u. And what does cos 2u integrate to? Well, I know that sine differentiates to cos, so I know that minus sine differentiates to minus cos. So I know that minus cos integrates to minus sine. So if that makes any sense. So this is going to be minus sine 2u. And we have to be careful because there should also be a constant on the outside. And that constant is 1/2. And the reason is if you differentiate 1/2 sine 2u, the 2 comes out because of the chain rule. And you have minus 1 times cos 2u, which is what's right here. So we need that 1/2 to be there because of the chain rule when you go backwards and differentiate. And we put the limits in. And the final step is to just evaluate. So I'm just going to rub out some of this stuff down here just so we have a bit more space. Okay, right. Plugging things in, we have b a over 2, open bracket. Let's do it all. So u, pi over 2, so pi over 2 is there. Minus 1/2 sine 2 times pi over 2 is pi. Okay, and then I'll do an extra bracket here. We're taking away the same thing but evaluating it at 0. But guys, u evaluated at 0 is 0, and sine of 2u is just sine of 0, which is just 0. So all of this just ends up being 0 basically, but I'll still write it out. 0 minus a half sine of 0 basically. But all of this is 0. That's all 0. Okay, so we have b a over 2 times pi over 2. What is sine of pi? Well, that's also 0. So that's just gone. This is 0. So this is it. Okay. And this is ba times pi. 2 times 2 is 4 over 4. And remember, that was just 1/4 of the entire ellipse. So we need to multiply this by 4 to get the entire area. So the area of an ellipse must be 4 times this, which is AB pi, or BA pi, whatever you want. And this is what we were trying to show that it was equal to. So just to be very clear, guys, this is not the easiest way to do this. There is an easier way if you know how to use parametric integration, but I just didn't want to do it because I wanted to show, because I think it's quite nice. We have the double angle formula, we're doing a trig substitution, we're doing quite a lot of work, and so it's just good integration revision, okay? But if you know parametric integration, this is a lot easier, and in the future I will make the same question, and I'll do it with parametric integration, and we'll see the difference. But anyway, guys, for now, thank you so much for watching. I do highly appreciate it, and I'll see you in the next video. Cheers.